All right, let's get started. So not a lot of people here today. Hopefully that's because everybody's off studying for the exam and is trying to watch the video later. But we're going to be forging ahead and talking about Project 3 today. So both parts of Project 3 are now on the website. Who's read part A yet? Okay, so a few people. So this will actually be a malloc assignment where you have to build your own malloc and free implementation. And I think a few people have already done this before, so we mixed it up a little bit, but for you it'll be a good review. And also we're turning it into a contest, so if you've done this before you could be more competitive. But it's just a good thing for everybody to know. And then for the kernel part, we're going to have you just change a few things about how virtual memory is managed. So I think it's useful if you do all these projects, you can really see how memory is managed across different layers of the stack, and it all starts to kind of make sense. So let's look at part A here. So this is just describing your interface. Well, this is the traditional interface. You're going to do something slightly different. It's actually kind of painful if you want to directly replace malloc because all these other libraries might use that. And if you get it wrong at all, then it's hard to have a partially working solution. So you're going to have calls that are similar to these, but with a slightly different prototype. Other things that are going to be different for yours is that you're just going to grab a lot of virtual memory when you first start. You're going to ask the OS for that, and then you're going to do all your allocations out of that. So you don't have to worry about, if you're starting to run out of space, asking for more memory from the kernel. You just have a fixed amount, and then you do the best you can with that, and if you can't do anything, then you just fail. So this is basically your malloc, this is your free, and then we have some other calls, mostly to help for debugging. So it says on here, let me see where this is. So you have a header file that you basically have to initialize. So let's go look at that now. So basically you have to implement this interface here. And I've implemented some stubs here to look at. So besides that, so I have my Meminet, memalloc, memfree, and so on, memavailable. And where's main? So and then I just have a little program that we'll eventually use for this. So one of the interesting things about this project is that you're going to learn a new way to link your code together. So everything we've been doing so far is called static linking, which basically means if you write all these different C files, they all get pulled together in one big binary, right? So let me show you what that looks like. So I have my files here, and I can just specify a bunch of files here on the command line, and I'll put those to main, maybe do some warnings, so that's fine, and I can run that. So that's not surprising, right? I haven't really implemented anything yet, but if you see in my mem.c, I just have hello world here. So we have our main file here that we've compiled, and let's do an object dump on that to see what's inside. Let me make this a little bit bigger. Okay, so lots of different stuff. Let me scroll down to the interesting pieces. So here you see, here's all the different functions in our mem.c file. We have our meminet, memalloc, and so on. And if we go farther down, we have our main. So this is all shoved together in one big thing. And this is, you can do libraries this way, but this is actually inconvenient, right? Because let's say you have a library such as malloc that might be used by many people. If they all have to compile that into their code, that's very wasteful, right? You have the same code and a lot of different binaries on your system. So instead of this static linking, where you just pile all your code together in one big binary, the alternative is dynamic linking, where your main file just says, I need to use this library, and then it will find it whenever it needs it, and everybody can use the same shared objects. So that's what I'm going to show you how to do. So if you go back to the website, there's lots of descriptions here for how to do this. So first, let me exit out of here. I'm going to remove main. Actually, I have a make file here, so I'm just going to do make clean. Okay, good. And the first thing we have to do is we're just going to compile our mem.c file with our malloc implementation. And it's pretty much like normal, except we're giving it this FPIC flag. And that just means position independent code. And we need to have that because it's dynamically loaded. So whenever we link with different things, it could end up in different places in the address space. So let me compile this here quick. Oh, and it already ran. So I have this mem.o file, and now what we have to do next is now that we have this position independent code in our .o file, we can compile it with this. And basically, I'm adding this shared flag, otherwise it's like before, and I'm creating a .so file for shared object. So nothing too crazy here. So I'm going to do that, and now I have my SO file here. And then I can just compile my main.c file by itself. So I'm going to show you some wrong ways to do that, just so you remember the additional flags you need. So I'm going to just do main.c and a warn all on that. And actually, let's try to send it somewhere. Oh. All right, so the first thing that we're seeing is that since we're just compiling it by itself, we get this error message that there's an undefined reference to Meminet. So basically what we can do to try to fix that, or one of the flags we need is we can say dash lmem, right? So you've probably seen dash lp thread before, or some of these other things. Maybe if you've used the math libraries, you have to do dash lm. But basically, we see that our SO file is called libmem1.so. So what we really want here is I actually just mem1. And kind of, it's just like a standard thing, right? Instead of the lib, we have just an L. So I'm going to run this. Okay, and it's still not happy. And now it's not happy because even though I'm saying the right name for the SO file, it doesn't know where to look for it. So to specify where to look for it, I can add this dash L flag. And this is specifying a new directory, and I just want the current directory. So I run that, and look, it compiles. And let me run this again. So here's another tricky thing. If I try to run this, I'm going to get this error, right, that it cannot open this file. And if I wanted to, I could actually see all the different SO files that my code depends on with this LDD program. So if I run this on main, I see that it depends on these 4 different SO files. So I don't know what all of these are, but you know libc.so, and it's having trouble finding this new one that I added. And there's an easy fix for this. How many of you are familiar with this path variable? So most people, right? So just to review, whenever you try to run a program on your computer, if you don't type the full path, it will search in all of these different directories that are separated by colons to see if it has that binary. So there's a very similar variable for .so files, and that variable is, I'm going to try to echo it, it's load library path. And right now it's not going to be set into anything. So that's my problem, right? It has a few default places, but I'm trying to set extra places in here, and it doesn't know where those are. So I need to set this thing, and I'm going to set, so I'm in bash, so I use the export command to update my environment variables, and I'm going to set that to the current directory. So let's try to look here now. So I'm going to do that, and I'm going to echo again, and now it's there. Let me go back to the website quick. So if you look on the website, the directions here are a little bit different. You're using the set environment, and that's because set environment is what you would use on the C shell, and I think some of the CSL accounts are still using the corn shell instead of bash. So how many people know that they have bash on their account? And how many people know that they have CSH? Okay, so maybe they switched at some point. I know, like when I was an undergrad, it was CSH, and then when they started creating new accounts, they did bash, but they didn't really change anybody from what they already were. So anyway, so rather than doing what's on the website, you want to be familiar with how to set these variables in bash and set it as I did here. And if I actually run the env program, I can see all these different environment variables that are set, and I see my load library path. So anyway, that's everything that we were doing so that we could go back to, well, actually I'm going to run LDD again. Remember before it said it couldn't find it, and now we see that it knows where this file is, right? It's just in the current directory, which means if I try to run my main program, it works just fine, right? And so let me do another thing here quick. I want to do the object dump again. Oops. So now if we were to scroll through all of this, we see that there's not any of the memory files, only our main. And so let me see here. Let's actually look at how big our main file is. So it's about 6.5 kilobytes. Let me compile it the other way we did before.
That's what I did before. Right, so we end up with a smaller binary doing it the new way. So let me just, so I added all these commands in the make file, so I'm just going to go back. So now we're back to the shared mode. So let me just double check that my binary is small again. Yes, it's small again. So this is kind of cool, right? A new way to link programs. And another cool thing about this is, let's say I wanted to modify my mem.c. So I'm just going to make a trivial change here. I'm going to say version 2 of hello world. You got to keep that updated. And actually, I forget what the commands are exactly. So I need to do this position independent code again on mem.c. So notice I'm not going to recompile main.c. I'm only recompiling mem.c. And I'm going to do my wall and error. So that's good. And I have a typo. So FPIC. Okay, and then I'm going to do the compilation to the .so file. So this is going to be shared, and the output is going to be lib mem1.so. And actually, did I switch over to 3? Sorry, I goofed that up. And I'm going to do mem.o. And let me just make sure my main file is right again. Okay, yeah, so I'm depending on my previous example, I was on a different version of the SO file. But anyway, now I'm linked with the right thing. So you see that I recompiled the mem.c, but I didn't recompile main. So now when I run main again, look, it updates. So you can imagine how this might be useful. Say there was some security hole in malloc or something. Somebody can very quickly push out just a new shared object, whereas instead if everybody did this static compilation, then everybody would have to recompile their program whenever there was a bug fix in a library. Right, so you can see how this is useful for both security and also having smaller files. Any questions so far? Okay. Oh yeah. Yeah, so he's just asking what does it mean for it to be position independent code? And basically if you're compiling all of your code at once into one big binary, you can know the addresses where everything will be. Right? So you can just do that during compilation. You can assign a fixed address to everything. But in this case, this SO file, different programs that link with it might need to load that SO file at different places in the address space. Right? Because different programs use different combinations of libraries, and we don't want to have to coordinate across all libraries to make sure they don't use the same addresses. Right? So we kind of have to leave it a little bit more general and say this code, we don't know where it's going to end up until we actually dynamically load it at runtime. We decide when we run it where it goes, not we don't decide when we actually compile it. Yeah.
So is that like all this like printf sort of thing done in the similar way?
Yeah, so if you see, I think printf is in libc, correct me if I'm wrong, but yeah, a lot of these libraries are in shared objects. So otherwise all our binaries would be huge, right, and it would be awful. So, other questions? Okay, so let's now start talking a little bit about how we'll actually implement malloc. So one of the strange things here, right, is that we need to have space to allocate all our objects from, and the way you're probably used to getting space is with malloc itself, but obviously since you're writing malloc, you can't use malloc. So instead, you have to directly ask the kernel for some new pages in virtual memory. And there's different ways to do that, but one of these ways is described on the website, and that is with mmap. So this is some strange code here, but I'll walk you through it. So basically what mmap does is it takes a file descriptor and it loads whatever file that is pointing to into memory, right? And this is just saying for our virtual memory what permissions we want on it. So we want to be able to read and write the things we malloc, but we don't want to be able to execute those things. And then we're saying private because we're the only ones that are using this space. And so what file exactly are we mapping in? We're mapping this dev/0. And this is a little bit strange if you aren't very familiar with a Unix environment. But basically in Unix, everything is a file. Like pipes are files, other status updates are files, like everything's a file. And they have a lot of fake files under dev that are just used for different purposes, right? So like there's a file called /dev/random, and if you read from that thing, you'll just get random bytes. But it's not like anybody ever wrote those bytes to the file, right? It's just a trick that the kernel itself is playing. I open this file and I read from it and I get data even though nobody ever wrote to it. And that's what this is, right? Nobody ever wrote a bunch of zeros to this file, but I can just open it and read as many zeros as I want from it. So that's what this is doing. So we have this fake file and we're mapping that in so we can get a large initialized region of all zeros. And then other things like if you, let me just show you, going a little bit on a tangent here. If I run mount, I can see that there's other things like this SDA1, that's my SATA disk, and this is a partition on it. So all of your disks are also these fake files, and it makes it really easy to write a file system on top of that. Okay, so anyway, so that's how we get our space, and I'm just setting this global variable for that. So all of the space you should be using for your implementation should be done in this way. You can have a few global variables if you want, but if you say have like a huge global array that you're storing things in, that would be little or no credit. If you call malloc, that's really no credit. So you have to use this space for everything, which is strange because you're going to have to do some bookkeeping to keep track of what space is allocated and freed. And normally when you do bookkeeping, you might have some data structure like a linked list. And when you ever create a new node in that linked list, you're probably used to calling malloc to get more space for that. But you can't call malloc anymore. So where do you store your linked list? You have to store that also in this free space. So what this might end up looking like is you might have, whoops.
Yeah.
What? Any questions?
No, I just didn't think about not using malloc for like the linked list.
Yeah, it'll be a pain, right? So we might have some struct, say node, and I'm actually going to do a type def right away. And we could have some info in here, say like size, and also we might want the next node. I'm not trying to go into a lot of detail. This is kind of just sketchy because I want you to think about it yourselves. I just want to get you on the right track. So when we first initialize this, we might have some, let me put this down here. We might have some head of our free space. So we'll say that's head. And when we get this free space, we might do something like this, right? Well, actually, we'll do this down here. So we already initialized our free space, and we might say this equals that space we're trying to allocate, right? So pretty much what this space will look like then is it might look something like this. When we first get started, we'll have a node here, and then lots of zeros, right? And maybe you might have some other type of node. We'll say node 2 for stuff that's allocated, and maybe you only need a size for that. But like let's say I called, so you just have to remember that all this free space is after your node. So like let's say I allocated something, I might have a node 2 here, and that might, we'll say that this is allocated, and then I might have to make another node here, right? So this node might keep track of free space, and this one might be keeping track of allocated space. Does that make sense? So basically you have all this area and you have to like carve out from it anything you need, right? So when I first initialized this, let me just show you what I might have done. I might have said that the head, and then what was my variable? I want to say the size of this thing. I might say the size of this equals the total size minus the size of my node itself, right? And then I can keep track of that free space. Any questions so far? So let's look at some other stuff. So let's say you first get started, and these aren't really nodes, but let's just say there's a lot of free space initially. And let's say you initially allocate something, you might use some of this
free space to be allocated, and then let's say you allocate again, you might get some more, and again, you might get some more. And then let's say people start calling free, right? Maybe they free this one, and then maybe they free this one, and free this one. If you aren't careful, you aren't going to end up with a free space of size 4. You're going to end up with 4 free spaces of size 1. So you really have to think about whenever you free something, how you can look through your list and combine it with other things that are adjacent, right? And I mean, you could do something simple where you just do a scan of the whole thing, or if you're clever and use some interesting data structures, well, not that interesting, like a linked list would probably be good enough. A doubly linked list would probably be good enough. You can do this faster, but we're kind of leaving that up to your discretion. And if you want to compete, you'll probably do something interesting. So that's the gist of it. I'm trying to think what else I want to tell you about. So you see that here that we're linking to the operating system book, and that's actually going to the same chapter that we talked about earlier. I think it was this memory management. Let me see if this is right. This is not right. Oh, here's a bunch of chapters here. Not segmentation. I forget which chapter it was. But anyway, let me go to it from here. Oops, I'm still on the wrong page. Let me go to it from here. We basically link to the operating systems book. And here we go. This chapter describes in great detail the kind of code you might want to write for your allocator. We went over this chapter in class, but now is a good time to go back and reread that when you start your project. What else? So, as I said, there's also a competition, and for your competition, there's going to be different types of workloads. This is really to drive home the point that if you understand the workload, you can build an optimized system for it. So you actually have to turn in 3 implementations of malloc, each for these 3 different workloads. And then you can also turn in optionally, so there's 5 .so files you could turn in. You could turn in these 2 libcontest.sos, and you must turn in these 3 for these actual 3 workloads. Yeah?
Sorry, great. It would inspire performance on those workloads?
On these 3?
Yeah.
I think for these 3, it's probably, so we haven't totally discussed the test yet, but I think it'll probably be if you meet some minimal standard, you'll pass, otherwise you'll fail. I don't think we're going to have it be like your speed directly influences your grade. That might change, right? Because Vijay is in charge of this project. But for instance, like one thing we might do is if we call a mix of allocate and free 1,000 times, and it fails after 800, and that we feel like that's too soon because you aren't coalescing very well, then you would have to be more clever about coalescing, right? So I mean, there's different implementations. If you have a really terrible implementation, it might fail a test even though it's not strictly wrong, right? But then you would lose points because you aren't doing the best you can on the project. So, but then for the competitions, I think one of these is based on time and one of these is based on space efficiency. So you can kind of choose, you could compete on both if you want, or you can try to choose what kind of scheduler you want, or what kind of allocator you want to write and go for that test. And then there's going to be free t-shirts for the winners. So questions about allocate before we move on to the kernel side of things? Okay, so let's first write a very simple program here. I'm going to go back to my main, and so this is not related to the allocator anymore, but I just want to give a simple example. I'm going to say L equals 0, and then actually I'm just going to say X. What will happen here? It should segfault, right? So let me just clarify something that I'm realizing a lot of people are getting hung up on the syntax for pointers.
this looks an awful lot. People think this means the same thing. Uh-oh, I laid it, there we go. People think that means the same thing as this, which does not mean the same. So if you think those are the same, you should probably be reviewing pointers some more. But basically what this is doing is this is not saying that x itself points to 0, but it's saying that this is not like assigning the thing that this. Okay, so we have a pointer here. We aren't changing the place, the value of the thing this points at, but we're actually changing the pointer itself. So the pointer is just pointing to null or 0. So yeah, this should segfault when we run it. So let me compile this quick. And great, so it segfaults as we wanted. So you may be surprised that this exact same program will work in xv6. So let's go over to xv6 and write a similar program. So I'm going to go to tester.c, and I'm going to write this to fault.c. And, oh, I already have it here. I forgot I was working through this before. Let me just do something simple first. All right, so this is basically the same example, right? We have a pointer pointing to 0, and we try to dereference it, and we're going to see what it contains. Actually, did I call it fault? I need to SSH in again so I can kill my QEMU. It's kind of annoying. You can't really shut down QEMU once it's started. You can only kill it from another terminal window. Okay, so I have my fault.c. I'm going to try to do an all pointer dereference, and I forgot to update this make file here. All right, so let's run this. And I run, oh, not tester. Okay, I guess it's the same because I copied it. Sorry. Okay, so there's fault, and I don't get any sort of segmentation fault. I just get a value here, right? That's kind of surprising. So what maybe you're seeing now is all of these segmentation faults you get, that's actually a feature that somebody spent some effort on to make sure you actually get that so you can debug your programs. So let me go back to my fault program. So if you wanted to, instead of just printing the integer, you could print off the hex value with %x. And that's maybe a little bit more informative here about what's going on. So I'm going to close this and do my make QEMU again. Oh, I'm running the wrong one again. Sorry. Okay, so remember this. Like, just memorize that quick for the next step of the demo. Maybe I'll write it down here, or at least the first parts of it. It's 83E5 something. Okay, and let me kill this. And so where is this coming from? Well, if you see here, under my code, I have this FS directory, and we haven't really looked at it that much yet, but that's just the things that get loaded by default in your xv6, kind of like your root file system when you first start. And so we see, of course, that our fault program is there, and we can actually do an object dump on that, just like we could on any other file. And let me pipe this to less. And what do we see here? We see 83, E5, 89, 55. And that's exactly the value that we were printing out, right? 83, E5, so on. So what's going on here? What's that? Yeah, that's exactly what's happening. Basically, normally in Linux, when you load your code, it's going to load it at some address other than 0. But silly xv6 here, it loads your code right starting at address 0. So that's actually a valid address. And you can see that the order is a little bit different, right? Because it's a little Indian machine. So you can review that if you don't recall that. But yeah, so basically, the goal of this assignment is that you need to change how programs are loaded so that they aren't loaded at address 0. Furthermore, you have to make sure that when somebody accesses address 0, that's not in the page table, so you'll get a fault. And once you get that fault, like, you know what's going on, and you can have your panic or exception or whatever, right? So that there's actually an error. So let's look at how we might do that. Yeah?
Is there a default location that like Unix and Linux loads it to, like that every program starts at?
Is it, you're wondering if it's at the same address every time?
Yeah.
I don't know if code ends up at the same address every time. The short answer is I'm not sure. I know for some other regions, they'll actually intentionally randomize it. They might do that for code too, but the idea of randomizing is that if somebody is trying to do an attack on the program and memory is in a different place each time, it's harder to attack. So I don't know if they do that for code as well. It's possible. Other questions? Okay, so that's the problem, right? We're loading code at address 0, and you have to change exec so that it doesn't do that anymore. So let's go look at exec. And this is some tricky code, but also some fun code. So this would probably be called after fork. So the first thing that it's doing here is that it's reading a file with this read_i. And it's an ELF file. That's just an executable format. You can go read about it if you want, but it's probably not the best use of your time. But one of the first things that we see it's doing is that it's setting up a page directory with this setup kvm. So I'm going to hop over to here, and we see that this is just creating an initial page table for us with the given layout. There's a lot of stuff in there. You can read through that if you like. But basically we're calling that, and we set up our initial address space, which is initially empty. And what we're doing first is that we're loading in some code into that address space. So basically, that vm.z file has a bunch of functions for manipulating your page tables, right? So you'll be wanting to use those functions. And you see here that they're first allocating some space in our virtual address space, and then they're doing this load uvm. And this IP thing points to a file. So they're basically loading the code into the address space, right? And a good tip for you is if when you're trying to read code like this, remember it's code, you can run it. Don't just stare at it forever. If you print some things out or change it in ways that you know won't break it, it's a lot easier to understand what's going on. So let's actually do that now. And basically we're allocating this space, and I want to see what the range is. So the two arguments are, so the size is kind of the start address in our virtual address space, and then this other thing is the end address. So I have these two values, and I'm just going to print off my two integers. I'll say, okay. And then we can see when we run this where these different programs are getting loaded into memory. Okay, so we see when we boot up that everything's getting loaded at position 0, and then this is its size. So we see that this first program, what is the first program? Init, yeah, exactly. It's init.c, and we see that program actually fits in just a single page. And what is this program that takes 2 pages to load into? It's a shell, right? And then if I run my fault, I see that also fits in just 1 page. Right, so basically your mission is to change that code so the start is 1 instead of 0. So then if somebody else accesses 0, they'll just get a seg fault. Make sense? So I think, I made a note of the things I should be reminding you of. Here's something I want to show you quick. So you notice that this fault program is 2052. Let me just show you that the file size is actually different. So if I load that, I see that this is actually bigger, right? Because these binaries, this ELF format, does not just have code in it, it has a lot of other stuff. So you wouldn't necessarily expect that to be the same. The ELF file should be bigger than this. What else do I need to show you? So another thing you have to change is in the user makefile. And over here, let me see what it's section start. So basically, this is just in the makefile. The makefile needs to know where your code starts in the virtual address space, just for some loading stuff when it first starts running it. So in addition to changing the exec.c file, you're also going to have to change this to be the new place where you're loading the code. So. Other interesting things in here. How many people have noticed so far in xv6 that you get a very strange error if you just return from main instead of exiting? How many people have run into that? Yeah, a few people. So and not everybody's paying attention because I've helped people with this and they didn't raise their hands. But anyway, that's because the entry function is main right here. And so normally in the Unix environment, right, when we've done the object dump before, maybe if you were paying close attention, you saw that there's a start function. And usually what will happen is that that start function calls main, and then when main returns, that just goes back to the start function, and then the start does a proper exit. So this isn't really an assignment, but if you wanted to for fun, you could go change your kernel and have this be start, and then you could have your start function. Where would your start function have to be? That would probably have to be in some library that's available to every binary, right? So maybe, I think there's like a user.h, you could put it there. And basically you could have an exit there and you could make x86 a little bit nicer, right? When somebody returns from main, it's actually reasonable instead of panicking. So that's an aside. Let me just go back to exec quick. And you actually see down here, if you really remember from the panic, like this is the return value from main, from the initial thing. So that's, when you see the panic, that's what you usually see, is that it's trying to access this address, all fs, which is invalid. So let me see here. Any questions so far before we talk about the next part of part 2? Yeah? No? Oh, okay. Where are we? So we were looking at this. So this is part 1. You can add this feature that your kernel will segfault more. That actually is a feature. And then we also have to do this stack rearrangement. And so this is kind of strange. xv6 doesn't use the same memory layout that we often use in our little pictures in OS class. In particular, they have the code at the small addresses, and then they have the stack, which is fixed size, and they just have one page for that. So it'd be kind of hard to write a recursive program in xv6 because you're going to run out of this stack very quickly, and then they have the heap that grows. Right? But I mean, it makes it a little bit easier to write the OS. But what you have to do, this is probably the hardest part of either this or P3A, is you have to move the stack. So instead of having the stack before the heap, now you have the stack after the heap, and there's a big gap here, and then the stack and heap are going to grow towards each other. Okay? So let's go back to the code and look at this. Okay, so you see some comments here. So we already looked at this stuff where we load the program into memory. This is loading the stack. First, it's allocating just a single page for it, right? That's why it's the current size plus this page size. And then it's doing all this stuff down here. What is this doing? It's just creating your argv, right? When the first program starts running, you have to have your argv arguments on the stack. So you have to have that, and then return values and so on. But basically what you have to do is instead of allocating this where it is, kind of just at the end of what's already been allocated, you have to allocate this at the end of your virtual address space and then let it grow up. So there's a few things that make this tricky, right? You can't just simply change this. One of the tricky things is that if I go to, there's a proc.h, let me see, I forget where this variable is. So they have this, for each process they have this size, they have this size variable. And basically the way they have it set up is that all virtual addresses from 0 to size are valid and nothing else is valid, right? But that's not sophisticated enough for you because you have a hole in your address space. So kind of you have a range of low addresses that are valid and a range of high addresses that are valid. So this is too simple for you, right? You can't just have this one variable. You're going to have multiple variables or some other form of bookkeeping so you can keep track of the fact that you have these two different valid ranges of virtual addresses. Okay? And that's kind of the ickiest part of this project because they use this size variable all over the code, and you have to go find all those places and fix those places. So let me just give you one simple example. So you guys all remember argint, I'm sure, where you just grab, a system call can grab an argument off the user stack. So that calls this other function fetchint, which is right here. And what is this doing? It's checking if the address is after is after size. Okay? So you can't really do that anymore. Like that check has to be a little sophisticated now. You have to say, is this address either in my allocated stack range or in my allocated heap range? Right? So that's going to be a bit of a pain. You have to grep through, find all those places, and fix all of them. The other thing that you have to do that's kind of tricky is that the stack and the heap grow in different ways. So when somebody wants to grow the heap, they can just do a system call and tell the kernel, hey, I want a bigger heap. And that's simple. For the stack, they don't really do that. They just call more functions and it keeps pushing it on. So you might see the stack trying to grow into unallocated regions of memory. Okay, they're just going to start using it. So what's going to happen when you use this unallocated regions of memory? It'll fault, right? So you're going to go into trap.c, and of course, like it's fine for the program to grow in that direction, right? But what we have to do is when we see that the stack is growing, you can tell, right? Because you know which page is being allocated, and you can tell that that's right at the end of where your stack is. When somebody tries to access that unallocated page and you trap to the OS, you should be allocating more memory for that, so you can just seamlessly let your stack grow, right? So that'll be a bit of a pain. So I think that's about it. So what do people have for questions? So this will be substantially harder than the scheduler, I think, but that's okay because you guys are substantially better programmers now in the kernel after doing that. So any questions? All right, well that's it then.